Hello again, this is Mr. Mack, and this is the second half of the video on the notes for session 2. And we're starting out with conditional probability. Now, we had a little bit of conditional probability at the end of the last one. Probability of A given B. The up and down line here means given. And the idea is that what we want to know is what is the probability that A will occur if we know that B, what's the probability that A occurred or will occur if we know that B has occurred or will occur. And it turns out that the formula for this is the probability of A intersect B. In other words, the probability that both of them occur over the probability that B occurs. Now, I spoke with you some about this last time. When we say given B, in other words, when you're computing a probability on the bottom, you put all of the things that could possibly happen. And if we know B has happened, then the probability of B goes on the bottom, and then the probability that they both occur goes on the top. That's a formula you probably should remember. Okay, and I'll let you read that stuff. Conditional probability works in the same way as simple probability. The only difference is we're provided with some prior knowledge, knowing that B has occurred, so we use that as the bottom of the fraction. Okay, now a couple of examples. A die is tossed. What is the probability that it is a 2? Well, that is probability of a 2 on a die is just one way for a 2 to happen. 6 things that could happen. After tossing a die, it is noted that an even number appeared. What is the probability that it is a 2? Well, the probability that it is a 2 given even would be one way on the top, because there's only one way to get a 2, out of 3 possibilities on the bottom. So the probability that a roll of a die is 2, given that the roll is even, is 1/3. Now I wrote this up above for you. This is a formal definition. Note, if A and B are mutually exclusive, then the probability of A given B is 0. This is kind of obvious, but guys, think about this for just a minute. If A and B are mutually exclusive, in other words, if we know that A and B can't occur at the same time, and we know B has occurred, then what's the probability that A occurred? Well, 0, okay? Now, from the above rule, we can also use the general multiplication rule. The probability of A intersect B is equal to the probability of A given B times the probability of B. Well, let's take a look at it. If we have probability A given B is equal to the probability of A intersect B over the probability of B, and if we multiply both sides of this equation by the probability of B, notice on the left-hand side we have probability A given B times the probability of B is equal to the probability of A intersect B. And I've got it turned around, but you see there. Now, I'm going to mention one other thing to you here also. Remember we were talking earlier about independent events. Now, if A and B are independent, remember, then the probability of A given B is the same thing as the probability of A. And this is something that a lot of places will teach as a test for independence. If the probability of A times the probability of B is equal to the probability of A intersect B, then the events are independent. And vice versa, if A and B are independent, then the probability of A times the probability of B is equal to the probability of A intersect B. So that's a good thing to know. Now let's take a look at a couple of examples here. Example 1, 2 dice are numbered two dice numbered 1 to 6 are rolled onto a table. Find the probability of obtaining a sum of 5 given that the sum is 7 or less. I need a rectangle again to give me some space to actually do these things. All right. Now, two dice are numbered 1 to 6 and they're rolled onto a table. Find the probability of attaining a sum of 5 given that the sum is 7 or less. Now, I think this is the first time we've really talked about dice, so let's do this right. If we roll two dice, we could get a 1, a 2, a 3, a 4, a 5, or a 6 on the first die. And then we could get, let's call that the red die, and we could get a 1, a 2, a 3, a 4, a 5, or a 6 on the green die. Now, if you were to just draw lines here, each point of intersection, actually I probably should do red lines this way just to be consistent. There we go. Each point of intersection of the lines would represent a point in the sample space. This point, for example, would represent 2 on the red die and 1 on the green die. Now, if you think about this a little bit, the sum of 5 is, let's get rid of this circle. A sum of 5 would be a 4 on the red die, a 1 on the green die, a 3 on the red die, a 2 on the green die, a 2 on the red die, a 3 on the green die, or a 4 on the red die and a 1 on the green die. In other words, it would be this diagonal here. And there are 4 points in that sample space. Now, so what is the probability that we get a 5, a sum of 5, given the sum is 7 or less? Well, now, this is a sum of 7 right here. This would be a sum of 6. I've already identified 5. This would be a sum of 4. This would be a sum of 3. And this would be a sum of 2. So if you'll notice, there are 6. Okay, so the probability of a 5 given a sum of 7 or less, on the top, there are 4 ways to get a 5. Now on the bottom, there are 6 ways to get a 7, 5 ways to get a 6, 4 ways to get a 5, 3 ways to get a 4. Let's see. 1, 2, 3, 4, 5, 6. 6 ways to get a 7, 5 ways to get a 6, 4 ways to get a 5, 3 ways to get a 4, 2 ways to get a 3, and 1 way to get a 2. There we go. I kind of got myself confused. So if we add these up, I think we get 15 on the bottom. So 4 on the top, 15 on the bottom. 4/15ths would be the probability of attaining a sum of 5, given that the sum is 7 or less. Now, I'm going to keep this grid, but I need to get rid of these circles. So let's these ovals. So let's see if I can do that without. Okay, and let's just, oh, no, not that. I need to select all of this. Let's see, can I get it that way? There we go. Maybe if I move that out of the way, try this again. I think maybe that'll do it. Yeah, okay, there we go. Oh. In case I need it again, I have it there. All right, now. And I seem to have lost my rectangle. There it is. Okay. Okay. So, example 2, two events A and B are such that the probability of A is 0.5, the probability of B is 0.3, and the probability of A union B is 0.6. Find the probability of A given B. Okay. Well, let's just go back to the Venn diagram here. Maybe this will work out nicely for us. We'll see in a minute. Here's A, here's B. Now, probability of A is 0.5, probability of B is 0.3, and the probability of A union B is 0.6. Well, let's call this X. So the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. That's always true. And so we can say 0.6 is equal to 0.5 plus 0.3 minus X. And so we get 0.6 equals 0.8 minus X. Subtract 0.8 from both sides. 0.2, negative 0.2 is equal to negative X. So X is equal to 0.2. Let's just put these in here. 0.2, 0.3, 0.1, 0.4. Okay, now find the probability of A given B. Now the probability of A given B is the probability of the intersection of A and B over the probability of B, or 2/3. Was there more? Okay, yes, find the probability of B given A. The probability of B given A, again, is the probability of the intersection of A and B over the probability of A. So we get 2/5. And find the probability of not A given B. Now, C, the probability of the complement of A given B. Now, first of all, you see the part A on this, the probability of A given B was 2/3. So the probability of not A given B is going to be 1/3. But let's take a look at that in more detail. The probability of not A intersect B would be everything that's outside A and inside B, which is 0.1, over the probability of A, which is, over the probability of B, I'm sorry, which is 0.3, so we get 1/3. But it should seem obvious to, or it should be obvious to you, that either A is going to occur or it isn't going to occur. So if you know B has occurred, and the probability A occurs when B occurs is 2/3, then the probability that A doesn't occur when B occurs has to be 1 minus 2/3 or 1/3. Okay, I hope I wasn't too confusing on that. Are A and B independent? Now, they would be independent if their intersection was the product of their probabilities. So on D, what we're going to do is we're going to take the probability of A, which is 0.5, and we're going to multiply by the probability of B, which is 0.3, and we get 0.15, which is not equal to 0.2. Therefore, A and B are not independent. All right. I'm going to erase this part up here. Okay, and now what do we have? We have a utility company asked 50 of its customers whether they pay their bills online or by mail. What is the probability that a customer pays the bill online given the customer's mail? So probability paying online given mail. Mail, not mail. Ooh, it's a little confusing. Okay, the number of non-females is 12 plus 8, or 20. That's what goes on the bottom. And the number of non-females who pay online, that's the intersection, is 12. So we get 12 over 20, which reduces to, what do we get, 3/5. I think that's it on that one. Yep, okay. A school system compiled the following information from a survey it sent to people who were juniors 10 years ago. 85% of those students graduated from high school. Of the students who graduated from high school, 90% were happy with their present jobs. Of the students who did not graduate from high school, 60% were happy with their present jobs. What's the probability that a person from the junior class 10 years ago graduated from high school and is happy with his or her present job? Okay, let's see. This is the same thing as asking what's the probability happy given graduate. What is the probability that a person from the junior class 10 years ago graduated from high school and is happy with his or her present job? Okay, that's not given. That's just happy and intersect graduated. Now, we've got 85% of the students graduated from high school. And of the, okay, let's, I don't know why, but I'm just having a little trouble. Here we've got happy, here we've got graduated. Okay, now, 85% of the students graduated from high school, so there's 0.85 inside here. Now, of the students who graduated from high school, 90% were happy. Okay, so 90% of this 85%, 0.9 of 0.85 is what goes in here. Now, let's see if we can figure out what that is. Oh, maybe not. 0.9 times 0.8 is 0.72 plus 0.045, 0.765. I think it's 0.765 here. So that would make this 0.085. I think so. And so let's just get the calculator here so that I'm not making horrible errors again. Okay, so 0.9 times 0.85, not plus, is 0.765. Okay, that's good. Now, if we subtract that from 0.85, we get 0.085. That's good. Now, let's see. of the students who did not graduate, 60% are happy with their present jobs. Okay, so now it said 85% graduated, so 0.15% didn't, and 60% of them are happy with their jobs, so that's 0.09. Okay, so the ones that didn't graduate and are happy would be 0.09. So that goes here. Now, the easiest way to get the ones that didn't graduate and aren't happy is to add together 0.09 and 0.85, which is what those other two circles would add up to. Oops. We get 0.94, so we get 0.06 out here. Now let's see if we can answer the question. What is the probability that a person from the junior class 10 years ago graduated from high school and is happy with his or her present job? That would be this region right here, 0.765. Now, given that the student is happy with his or her present job, what is the probability they did not graduate from high school? Well, the probability that they're happy would be 0.765 plus 0.09, and the probability they did not graduate from high school is 0.09. So we have calculator, where is that? Here it is. Let's move that over here. We have 0.09 divide, in parentheses, 0.765 plus 0.09. And we could actually ask for that as a fraction. 2/19. Okay. For the next example, okay, now we're going to be dealing with two-way tables. Two-way tables can give you data or information, and you have to kind of look at the information, look at the table, and read the question that's asked to figure out how many are this or that or the other thing. Let's see. Okay, let's go down to the first example here. Use the table below, which gives area of concentration of 400 students at a small college. Okay, on the rows we've got students that are natural science majors, students that are social science majors, students that are humanities majors, and we have the totals, and then we have freshmen, sophomore, juniors, and seniors in the columns. Okay, now, if a student is selected at random, what is the probability the student's area of concentration is the natural sciences? Okay, now, there are 147 students whose concentration is the natural sciences. And if we're selecting a student at random, there are 400 students. So the answer to I would be 147 over 400. If a student is a freshman in the social, okay, okay. A, if the student is selected at random, what is the probability the student is a freshman in the social sciences? Okay, a freshman in the social sciences, there are 20 of those. And again, we're selecting a student at random, so the bottom is 400, 200, 20 over 400, or 1/20th. Okay. B, if a sophomore is selected at random, what is the probability that his or her area of concentration is the humanities? Now, our denominator is going to be sophomores, which is, there's 100 of those. And the area of concentration is the humanities. That would be the intersection of sophomore and humanities, which is 40. So we get 4/10 or 2/5. Okay, what is the probability that a senior's area of concentration is the natural sciences? So on the bottom, we're going to put seniors. There's 90 of those. And the concentration being the natural sciences, there's 29 seniors who concentrate in natural sciences, so 29/90ths. We got another one there? Yeah, what is the probability that a student in the natural sciences is a senior? Okay, now we have students in the natural sciences is the denominator, which would be 147, and we want to know what the probability is that that student is the student in the natural sciences is a senior. And so in the natural sciences, the intersection of natural science and senior is 29. So we get 29 over 147. I think that takes care of the questions on this 2-8. No, it doesn't. What is the probability that a junior's area of concentration is humanities? Okay, so we'll go back up here. A junior's concentration is humanities. Now, there are 100 juniors, and the juniors that concentrate in humanities are 39. So 39 over 100. Do we have another one? What is the we have, whoa, same question marches on and on. What is the probability that a student in the humanities is a junior? Okay, now, in the humanities, we have 156 students. So the denominator would be 156. And what's the probability that that student is a junior? Well, that's 39 over 156. A student is, what is the probability a student is selected at random? Are the events student is a junior and student is in the humanities independent? Student is a junior and student is in the humanities. Are they independent? Well, student is a junior is 100 over 400 or 1/4. Student is junior. Student is in humanities. There are 156 students in humanities, and the juniors in humanities are 37. Student is a junior, junior in humanities. No, student is in humanities. Sorry about this. Student is a junior is 1/4. Student is in humanities is 156 over 400. Now, the probability that a student selected at random is a junior in humanities is going to be 39 over 156. So the question is, when we multiply 1/4 times 156 over 400, do we get 39 over 156? Well, let's see. 1 divide 4 times 156 divide 400, and that's equal to that. Now 39 divide 156 is not the same thing, so no. The answer to the question, are they independent, is no. A student is selected at random. Are the events student is a junior and student is in natural sciences independent? Let me do this. Okay. A student is selected at random. Are the events student is a junior? Now, probability the student is a junior is, once again, 100 over 400 or 1/4. Probability student is in natural sciences is 147 over 400. Are the event student is a junior and student is in natural sciences independent? Well, if 1/4, the probability that the student is a junior intersect natural sciences is equal to 33 over 100. So let's see what we get. We have 1/4 times 147 over 400, and that's going to be 147 over 1600, which is not, no, it's not. These two are not equal, so therefore the answer again is no. Okay, according to the National Center for Health Statistics, in December of 2008, 78% of U.S. households had traditional landline telephones, 80% had cell phones, and 60% had both. Suppose we randomly selected a household in December of 2008. Make a two-way table that displays the sample of this chance process. Okay, what have we got? We've got landline, we have cell phone, and both. Not really seeing how to make a two-way table out of this. According to the National Center, 78% of U.S. households had traditional landlines, 80% had cell phones. Okay, let's try this. Landline, cell phone, both. Have not. So landline, 0.78, 0.22. Cell phone, 0.8, 0.2. 0.6, 0.4. Construct a Venn diagram to represent the outcomes of this chance process. Okay, now that might be a little bit easier. We got landline, cell phone. So we have a 0.6 here. We have a 0.18 here. We have a 0.2 here. And 0.6, 0.8, um, 0.6, 0.8, 0.98, 0.02. Okay, it says find the probability that a household has at least one of these two types of phones. Well, the easiest way to do that would be to look at the Venn diagram here, and everyone except this 2% are inside one circle or the other, so the probability that the household has at least one of the two types is 98%. Find the probability that the household has neither type of phone. Well, that's 0.02%. And finally, find the probability the household has cell phones only. That would be 20%. And we're finished with that one. Thank goodness. Okay, let's try. Find the probability that an individual does not get cancer given that he does not smoke. Here are the counts of earned degrees in the United States in a recent year, classified by level, by sex of the degree recipient. You know what? I think that line, find the probability that an individual does not get cancer, I don't think that has to do with this problem. So let's just cross through that. If it turns out that we are actually using it, we'll come back to it. But I think that's misplaced or a typo or something. Now it says, if you choose a degree recipient at random, what's the probability that the person you choose is a woman? Okay, now, a degree recipient at random. Now, that means we're talking about total number of degrees. That's 1626 on the bottom. What's the probability the person is a woman? That would be the same as female. We get 856. So 856 over 1626. You can ask your calculator to reduce that fraction for you, but let's just move on. What's the probability that a randomly chosen degree recipient is a man? Well, that would be 770 over the same 1626. Okay. What is the conditional probability that you choose a woman given the person received a professional degree? Okay. Okay, we want probability woman given professional degree. Okay, now the probability of woman intersect professional degree is 30, and the probability of a professional degree is 74. So 30 over 74. Oops. What is the conditional probability that a person chosen receives a bachelor's degree given that he's a man? So probability bachelor's given man. Okay, now there are the person receives a bachelor's degree given that the person is a man. The probability the person is a man, or the number of men, is 770. That's what goes on the bottom. And the probability of man intersect bachelor's degree is 529. So 529 would go on the top. And are the events choose a woman and choose a professional degree recipient independent? How do you know? Okay. Choose a woman, choose a professional degree recipient. Okay. Probability the person is a woman is, let's go up there and see, 856 over 1626. Probability a person is a professional degree recipient is 74 over 1626. Probability professional degree, what did I say, 74 over 1626? Let me just check that to make sure. Okay. Now, what is the probability woman and professional degree? Well, that would be, what would that be? 30 over 1626. Now, if 856 over 1626 times 74 over 1626 is equal to that, then we would say yes. And once again, let's do a little bit of work on the calculator here. 856 divides 1626 times 74 over 1626 is that, and 30 over 1626 is that. So the answer again is no, since the product of their probabilities is not equal to the probability of their intersection. Those are not independent events. Okay, and we're done.